Woohoo! It's a great day to learn some geometry. I'm Miss Leg Battles, and I'm here today to talk to you about circles. This is just a couple of small units in our study of circles. We're going to be talking about tangents and chords and secants. The vocabulary is very important in this unit, so I want to start with that. In the first illustration here, notice that line AB is a tangent to the circle. A tangent to a circle is a line in the plane of the circle that intersects the circle in exactly one point. The point where the circle and a tangent intersect is called the point of tangency, and in this illustration it is point P. In the second illustration, there is a chord. A chord is a segment whose endpoints are on the circle, and the illustration shows chord CD. Another common chord would be the diameter. We know that as the chords get further away from the center, they get shorter, and the largest chord of a circle is its diameter. In the final illustration, it is a secant, line EF. A secant is a line that intersects a circle at 2 points. It's a chord that just keeps going. There's a couple of rules about tangent lines that we need to know. A line that's tangent to a circle is perpendicular to the radius at the point of tangency, and the converse of that is also true. So a good way to say that is a line is a tangent to a circle if and only if it is perpendicular to the radius at the point of tangency. So that's what's illustrated in the first diagram. In the second diagram, this rule is illustrated. From any point outside a circle, you can draw two segments tangent to a circle, and those segments are congruent. And now we have some rules about chords and arcs. First of all, congruent chords have congruent central angles and congruent arcs. Next, congruent chords are equidistant from the center. That means they're the same distance from the center. A diameter that bisects a chord that's not a diameter is perpendicular to the chord, and the perpendicular bisector of a chord contains the center of the circle. Now we have a few problems to work for examples. In the figure to the right, if AC equals 22 and BC equals 19, what is the radius? So let's get this labeled. First of all, AC is 22. Next, BC is 19. What is the radius? So I'm going to mark this X because segment BA would represent the radius of the circle. So I hope you're thinking this means, because we have a tangent here and this is a right angle, that means we're going to need to use the Pythagorean theorem. I like to say Pythagorize. So when we substitute in, notice that 22 is the hypotenuse. So x squared plus 19 squared equals 22 squared. So x squared is equal to 22 squared minus 19 squared, and that's 123. So to find x, we just need the square root of 123. On this one, we've been asked to round to the nearest tenth. So if we put that in our calculator, we'll find that's about 11.1. In this next example, notice it says that the segment that appears to be tangent is a tangent. O is the center of the circle, and we're looking for the value of x, which is an angle measure. Now, the thing that you might not notice right away is since this angle is 64, I know that this is an isosceles triangle because radii of the same circle are going to be congruent. So if that angle is 64, then this one would have to be 64 as well. And we can find that central angle, that would be angle O, by using the triangle angle sum theorem. If we just say 180 minus the two angles that we know, 64 and 64, that'll give me the angle that's left, which is 52. So this angle is 52. Now, that's going to help me when I look at this whole big triangle here. In this whole big triangle, remember, this is a tangent, so that makes this angle a right angle. So in this big right triangle, I can find x, the missing angle, using the triangle angle sum theorem again. I know these three angles should add up to 180, so if I subtract out, the 90-degree angle, the right angle that I know is right because of the tangent, and then the 52-degree angle that I found, that's going to leave me with 38. So x in this problem is 38 degrees. In this next example, our directions are just to find x to the nearest tenth. What I notice right away, since a tangent is illustrated, is that we have a right triangle. And we're looking for one of the legs, but also, remember, these would have to be the same measure, both of these x's, because they are radii of the same circle. So let's Pythagorize again. One leg of the triangle is x. Another leg of the triangle is 10. And the hypotenuse, we can call the hypotenuse 7 plus x, or x plus 7. So when I put all this in the Pythagorean theorem and simplify, I get x squared plus 100. And remember, when you square a binomial, we're going to square the first term, twice the product, square the last term. If you don't believe me, you could just take this and write it down twice and use the full method. And you combine those middle-like terms and you get x squared plus 14x plus 49. Now, the next thing I notice is when I go to get everything on one side and I subtract x squared from both sides, they're just gone. So that leaves me with 100. Let's get the 14x by itself. So let's subtract 49. So that gives me 51 equals 14x. And to get x by itself, I'm just going to divide both sides by 14. And that leaves me with x to the nearest tenth would be about 3.6. Another example that I've chosen says find the perimeter. Well, I need you to remember the rule that we talked about, that the tangents that are drawn from the same exterior point are congruent. So this segment is congruent to this segment. That makes this also 19 centimeters. Okay. We also know that this segment is congruent to this one. So this would be 8. For the same reason, this one is 6, and this one is 9. So now we have every single length around the polygon, so we can find the perimeter pretty easily now. It would be, let's see, we have 2 lengths that are 19. We have 2 lengths that are 8. We have 2 lengths that are 6. And then we have 2 lengths that are 9. So let's add all these up. My handy dandy calculator, I believe it's 84 centimeters. Check my work on that one. And this brings me to the last example. You know, we know that if this is perpendicular, that this 6 is divided into 2 3s. So I know these lengths. But I'm not really sure how to figure out the other. You know, this problem really ends up depending on you being able to draw the radius in a place that's helpful for you to work the problem. So if I draw the radius here, well, that's a great place for the radius because now I have a right triangle. And if the radius is x down here, well, the radius is x anywhere because it's going to be the same within that circle. So, it's another good old Pythagorean theorem problem. Let's Pythagorize. We're looking for the hypotenuse of a right triangle. So I'm going to put my made-up word here because I like it. Pythagorize. That's going to give me the hypotenuse, which is x. X squared equals 3 squared plus 3.1 squared. And that gives me x squared equals 18.61. Now I'm going to have to take the square root to find x. And it says we're to round to the nearest tenth. So again, using my handy dandy calculator, I find that to be about 4.3. Hope this has been helpful. It's been a great day to learn about some circles, and we've got more to come. Have a great day.